Okay, so here, this will be part of the lab document, but I'm going to walk you through some of the examples together. Okay, so the first example is we're going to estimate pi. And this is a really crude way to estimate pi, and it's really computationally extensive, and there's better ways to estimate pi. Google it sometime, it's pretty interesting how people actually get the pi to the nearest 1/1,000,000th decimal point. This is not the way to do it, but it's a good example of Monte Carlo simulation. So we can estimate pi by comparing, I'll just show you. We can estimate pi by comparing, we can simulate randomly points of x, y within the bounds of 0 to 1. So x can be between 0 and 1, y can be between 0 and 1. And if we draw a square that has a side of equal to 1, the area of that square is 1, right? 1 by 1 is 1. 1 times 1 is 1. And if we inscribe a circle within that square with a radius of 0.5, we can then simulate a bunch of random points and count up the number of points that fell in the circle versus that fell outside the circle and in the square. Now, the ratio of the area of the circle to the area of the square is 4 pi. You can go ahead and write that out yourself and figure it out, but that's what the ratio is if the radius is 0.5 of that circle. Now, we can determine the distance, or we can determine if a point is inside the circle or not by measuring its distance. And here's the distance equation for the origin centered at 0.5, 0.5. And if that's less than or equal to 0.5, then we're inside the circle. So we're estimating the area of the circle. We could say that the number of points that fall in the circle is going to be proportional to its area. And so it's just a factor of the area. And then we can estimate pi by counting up the number of points that fall in the circle, dividing by that by the number of points that fall in the square, multiplying it by 4, and that's going to be our estimate of pi. So as our points approach infinity, we're going to eventually get pi to a pretty good precision. So here's the code to do it. I'm going to do it for different values of n. So n from 1,000 all the way to 1,000,000. I'm going to set up an empty vector for pi estimate, and it's going to give us estimates of pi for these different samples.
Hey Joel,
yeah,
are you showing us what it's typed out as? Because all we can see is the PDF still of like just the top of the lab.
Can you see me highlighting text in the PDF?
No.
Okay, let's see. New share. Monte Carlo. Oh, here we go. There we go. Is that?
There you go. Yeah.
Okay, great. So I meant to show you this. So this is what that would look like, that circle inside of the square. The blue points are outside of the circle, the red points are inside the circle. And so our area of the circle divided by the area of the square is equal to pi over 4. And then if we calculate the number of points in the circle, divide that by the number of points in the square, multiply it by 4, that's our estimate of pi. Thanks. Sorry, guys. Got 2 screens here, and apparently things can get mixed up. Okay, so just to run you through this simulation, I set up different numbers of n, so different numbers of points that we're going to simulate. So 1,000 all the way to 1,000,000. I set up an empty vector for pi estimate. So when I do numeric, that makes a vector with the length of n, which is 4. So it's going to give me 4 empty spots. So now here's a little loop that I set up to run it through each of these number of samples from 1,000 to 1,000,000. So x, y, run if. So R is for random. UNIF is for uniform. So the uniform distribution is simply equal probability of any points between 0 and 1. So it's just a flat PDF. And so that means if I give it 1,000 For n, it'll give me 1,000 random values between 0 and 1 that have equal probability of occurring. So there's no curve here. It's just totally flat, equal chance. So I do that for x and y. Then I identify which points are within the circle by comparing the xy coordinates with the distance of xy coordinates from the origin of 0.5, 0.5. And so I get true and false for that. And then I just sum up the points that we have in the circle, divide that by the total number of points, which is all the points in the square, and multiply that by 4. So this is what it comes out to be. Here's 1,000 points, 10,000, 100,000, and then 1 million. And you can see our estimates of pi, even at 1 million, we're only estimating pi to the nearest thousandth accurately. So this is a pretty crude method, like I said. Here's what it looks like if we're going to go all the way to 100 million. And I didn't actually include that value. I should include that value. So if we go out to 100 million, here's pi at 3.14125 or whatever it is. We had a student last year who could write pi out to the nearest, I think, 50 decimal places. It was crazy. Anyway, so by the time we get to about 100 million simulations, we're pretty dang close. And I don't know to what decimal point it is, but you can see how it converges. So this is kind of a Monte Carlo way to estimate pi in a crude way. And just wanted to kind of show that as an example.
Does it ever overestimate it?
Does it ever overestimate pi? Yeah, you can see it does a little bit over here.
Okay.
Yeah, but mostly it's underestimating. Yeah, so the method is a little bit biased too, as you can see. Okay, so here's just the example that I went over just now when we're writing things down and looking at the paper. Here's our equation for the wave height z as a function of fetch, the depth of the reservoir, and our velocity of the wind. So instead of just the velocity having a distribution, now depth has a distribution and fetch has a distribution. The fetch distribution is normal, the depth distribution is log normal. We're not dealing with what are the, actually I made it normal in here, so it doesn't matter, it's just an example. So to do this, we're gonna say, okay, we'll set up our number of simulations, so n is equal to 10,000 simulations. And then we'll set up our distributions for each of the parameters. So fetch our norm with a mean and a standard deviation that we're given. Depth, I forgot to put our L norm here, so, but again, it doesn't matter, we're just doing this for illustration. So depth is our norm with n simulations, mean and standard deviation. And our velocity follows the exponential distribution and simulations, and then here's our lambda value. So 10 is the average speed, and then we do 1/10 as the parameter for the exponential distribution. When we do R, so these are functions in R. When we put R in front of the norm, that means we're doing random, so we're getting a random sample. So these are built-in functions you can use to simulate these distributions. So what I get then is a string of 10,000 values sampled from the distributions of F, D, and V. And I can plug that into the equation for Z and get a distribution for Z. And so that's what this looks like. This is our distribution of Z, which is probably pretty similar to what you guys got for your other problems, but know that this is not an exponential distribution as it was before. So from here, we could say, okay, now that Z is this kind of more complicated distribution, let's ask questions about what's the probability of overtopping or getting a wave of a certain height or something like that. Okay, now here's a different problem, and we're going to use, we have two more examples to go through. So this is kind of a similar setup as the previous problem, and then we'll take this problem kind of to the next level and do that kind of multi-layer simulation. Okay, so we have a building, and this building has a structure and a foundation. And the structure and foundation were built to withstand wind-induced pressure. So when the wind blows, it moves around the building and it causes a pressure on the building. So that pressure then is translated to, you know, a pressure on the elements of the structure as well as the foundation and its footings. So the capacity or for pressure force, these are pressure terms for the superstructure is 40 psf, and for the foundation it's 30 psf. So if we get a wind load that induces a pressure on the building that's greater than this, then we have failures of the foundation or the structure. And then we can model the pressure as this function, so 1.165 e to the negative 3 times c, which is the drag coefficient, times v squared, which is the velocity of the wind. And this gives us pressure in psf. V is going to be the maximum wind speed in a given year. Okay, so we'll say V follows an exponential distribution with an average annual maximum wind speed of 25. So that's our exponential distribution. And then our drag coefficient, we'll say, you know, because maybe buildings are a little not perfect, cylinders or whatever, the drag coefficient is uncertain, and it follows a normal distribution with a mean of 1.8 and a standard deviation of 0.5. Okay, so just as before, we'll simulate the value of wind pressure. And so that's what we did here. So we just said V is random exponential distribution for 10,000 simulations. C is a normal distribution. We'll do 10,000 simulations. So we'll just plug those values into P, and then we'll get a distribution of all these parameters. So here's our distribution of V as a histogram. Here's our distribution of C, the drag coefficient. And then here's our histogram of the pressures induced by V from the wind speed based on our uncertain drag coefficient and our variable wind speed. Okay, so just as before, that's all we did. And now we can actually do some calculations here. So here's what that PDF looks like. You can make a histogram kind of look like a PDF by using this density function right here. So I just put in the vector P, all those different values from the simulation, and it drew this. It kind of fits a smooth curve to it. And here's the cumulative distribution function for it as well. So now we can calculate the probability that the foundation or the superstructure will fail due to a wind event in a given year. So what I just did is I said, okay, here P is a vector of 10,000 values of potential pressures that we get from wind. So how many of those values are going to be greater than the pressure threshold for a superstructure failure? So I did basically sum of P's greater than RS. That gives me a string of 10,000 true falses. And true values take on a value of 1, falses take on a value of 0 in R. So if I sum those up, I just get the proportion of values in that distribution that are greater than the threshold for failure. So I divide that by n and I get a probability. So this is the annual chance probability of failure for the superstructure, and then the same thing for the foundation. So pretty tiny values, but now I want to know what's the probability of failure over the design life. And that's when I use the risk equation. So we've used the risk equation previously. The risk of failure is equal to 1 minus p to the n, where R is the risk of failure from an event, with that event having an annual exceedance probability P, which we just calculated here, over n years. So I plug these values in, and then I calculate the probability over 50 years, which is actually 20%. I have a typo here. I didn't give you the probability of the foundation failure, but I'll correct that. But it's the same equation. Okay, so we took basically we simulated a derived distribution, and then we asked some design or some probability questions of that, and then we did to actually calculate the probabilities by summing up values that are above certain values that we're interested in. So you could think of this as if our RS value right here, we defined it above here. So RS is equal to 40 PSF. So if we go to 40 PSF, we hit that cumulative distribution function here. We draw across, and then we do 1 minus that value, and that's what gave us this tiny 0.0048 value.
Is that the way you're calculating that probability? Can you pull that from like a histogram or a PDF that same way?
So probably it's not really directly because you don't have an equation, right? Before we were dealing with the world where we had an equation and we could just use that equation to solve. That's what you guys did in lab 4. You just use that equation to solve for the wave height given a certain probability, right? Or vice versa. Put a probability in, get a wave height. That's when you have an equation. Now we don't have an equation. We just have this simulation of values. And so the way I did it was I just said, give me the proportion of values that are greater than RS, this threshold, this failure threshold. So if you give me the proportion of that, it's basically like the percentile. So we're looking at percentiles essentially of a data set, and that's how we calculate the probabilities.
Okay, and this is telling you the probability that a foundation or structure fails in a given year because you're taking the probability of getting a wind load greater than something, but that's kind of like it's like a 1-year design, but it could be like a 100-year design. It's the same sort of deal, right? Just in a 1-year design spectrum, because you don't know if you'll get that or not type of deal, right?
Yeah, and so the way I've defined this problem is I said that the V distribution is the distribution of wind in a given year. And so what I said is, okay, so this is so P is the distribution of pressures. Here's P, the distribution of P. This is the distribution of pressures in a given year. And so now I have this P vector, which is just a vector of values. It's a distribution. It's a 10,000 values of P that you would expect to see on average in a given year. So I just said how many of those are actually bigger than that threshold. How many of those values are bigger than that threshold, and divide it by n to get the frequency.
Okay.
So that's my annual chance of exceeding RS. And then I plug that into the risk equation to get the design life or 50-year probability of seeing something equal to or greater than that particular pressure.
Okay.
So very, very similar to what you guys did in lab 4. You calculated a probability, an annual probability, and then you plug that into the risk equation to calculate the lifetime probability. Any other questions on this before I move on to the further into the rabbit hole? Okay. Okay, so for our final example, we're looking at epistemic uncertainty. And this is basically what I said up front in the lecture. So previously we had V and C were uncertain, right? And we said V follows that exponential distribution, and C follows a normal distribution with a mean and standard deviation. Now we're going to say that the parameters of the parameters. So we have the parameters of pressure, C and V, coefficient of variation and velocity, and then we have the parameters of the distribution of the parameters of pressure. So we're kind of one level in here. So now we're saying, so the mean of the drag coefficient is mu C, and we're saying that's uncertain. And it has a coefficient of variation of 0.3. We're saying lambda is uncertain, and lambda is 1 over the 25 miles per hour, the average wind speed. And lambda has a coefficient of variation of 0.15. So now what we're going to do is first we're going to simulate the uncertainty of mean of the coefficient of variation and lambda. We're saying the parameters have uncertainty, and you could imagine. So this is epistemic uncertainty. It just means that, well, when we're measuring the drag coefficient, it's a hard thing to measure. You got to use a wind tunnel, or you got to go to a book and read a value, or do some calculation, and it's all based on data. It's all based on lab data. And that lab data, anytime we make a measurement, it's going to be inherently uncertain. And so we're just saying that these mean values that we're using are going to be uncertain, and we need to account for that uncertainty. Okay, so I'll break it down to a couple of steps. So first, we'll simulate the distributions of the parameter mu, C, and lambda. And I'm just going to say that N is going to have a normal distribution. We'll do 1,000 simulations. The mean is 1, and then the standard deviation is going to be the coefficient of variation of mu C. And then the same for lambda. And you'll see why I said the mean is 1 here in a second. Okay, we'll create some empty vectors, and then now we're going to do a loop. And so the way this loop works is we're going to do 1,000 simulations. So N is 1,000. And what I'm going to do is I'm going to plug in the distributions for these uncertain parameters into the distribution for our coefficient C, our drag coefficient, and our velocity. And so the way that works is I went up here, I got a sample of 1,000 from a normal distribution for mu C, and 1,000 from a normal distribution for lambda. So I'm going to go in here, I'm going to go from 1 to 1,000. And so when I equals 1, that first iteration of the loop, I'm going to get 1,000 samples of C with the first value of our distribution of mu of C. And so I do 1.8, which is the mean of our drag coefficient, times this distribution, which has a mean of 1. And then I give it a standard deviation as originally described. So now I'm going to get 1,000 values of C with that first sample of our mu of C. And then I'll do the same for velocity. I'll get 1,000 simulations with the exponential distribution with that first sample from our normal distribution for lambda. Okay, then I'll calculate the pressure, and I'll get 1,000 simulations of pressure. And now what I'm going to do is every time I run this loop, I'm going to just append those 1,000 simulations. And so I'm going to do this 1,000 times. This loop is going to run for 1,000 times. And each time I run through the loop, I'm going to get the next sample of the mean from my mean distribution, and I'm going to get the next sample from my lambda distribution. And so I'll end up with $1 million. I'm going to end up with 1 million simulations of P. So 1,000 times. And now P it'll contain the uncertainty not only in our coefficient of variation and our velocity, but also the uncertainty of those variables. So this is the kind of double simulation here. So I'll plot that, and this is what our PDF looks like. It's a little bit different. It's going to be kind of more variable, meaning it's going to be kind of thicker than the PDF that we had from before.